This formula from Thursday is a future value of M with payments of J. And by working this out, we figured out what the time is in terms of the interest. But notice that that interest becomes force of interest when we actually work out the calculation. If I do the same thing for the present value, I would start with a present value of L sorry, is that right? Yes, and payments of K. And I could work through the same process. And I can end up with a similar formulation for time, for N. But I actually find this one to be less common. And again, it's the same algebraic manipulations to get the N out of that piece. Let's consider an example. I have a future value of 1,000, an interest rate of 0.08. Wait a minute, that I superscript 2 means that we've got a nominal rate of 4% twice a year. So let's just set that up right there on that first formula. If I make a regular payment of 50, then how long is it going to take me to pay this off? Now, this makes sense. This is a legitimate question. I can put away $50 every 6 months or 50 whatever every 6 months. How long until I have 1,000 at an interest rate of 8? Set it up exactly like this. All right. 1,000 divided by 50. And divide. So 20 equals 1.04 to the N minus 1 over 0.04. Multiply that up, I get 0.8. 1.04 to the N minus 1, 1.8, 1.04 to the N. So now to get N, I take a logarithm. ln 1.8 equals ln 1.04 to the N. But when I take a logarithm, powers jump out front. N times ln 1.04. So I divide. Give me a number. Be careful, that's wet back there. Looks like they wiped everything down and didn't quite wipe it up properly. What you got for that? 14.98. All right, that's not an even number of payments. So we have to make a decision. Are we going to make 14 payments and then pay a little more on the end? Or are we going to make 15 payments and pay a little less on the end? Because I need to make between 14 and 15, right? So what happens if I make 14 payments? Well, the future value of 14 payments would be that value. Now, I'm going to cheat 100% here. I'm going to do that on here. Using the financial application in the TVM solver, I can say I'm going to make 14 payments at 8% a year. Present value is 0. My payment is 50, and I'm doing 2 a year. Work out the future value. And I come up short, right? Call it 914.60. If I do that, then my last payment isn't $50 to get to 1,000. My last payment shouldn't be $50. My last payment should be more, right? I'm going to need to make an 80. I'm going to be short 85 bucks. I could make 15 payments. If I make 15 payments, just change this number of payments. Go back down and solve for the future value. And I see I come up $1 extra, $1.20. So I'd be a little bit over, closer to 15 than 14. I think I'm safer if I'm treating this like a sinking fund and my goal is to actually finish this out. I know what the last payment should be. In this case, I could technically make a last payment of 48 and change instead of making a last payment of 50, right? And here I can make a last payment of 85 instead of making a last payment of 50. If I have a large ending payment or an oversized ending payment, we call it a balloon payment. If we have one that's smaller, we call it a drop payment. Until the 1950s, 60s, almost every mortgage on the face of the planet was a balloon mortgage. If you bought a car, a house, your payment structure was you'd make payments every month and then you just owe the balance at the end. That was a balloon style. And most mortgages were 5 years, 6 years. They were not 15 or 30. The idea of doing steady level payments for a longer period of time came out of World War II and the return of all of these soldiers from overseas. But the 30-year mortgage is a fairly recent historical idea.
When you did the last payments by you're missing one.
Right, I came up short if I just make the regular payment, so let's make a slightly larger payment. Or I came in over, let's make a slightly smaller payment. If solving algebraically is a pain in the ass, I mean, I got really lucky to do this in a nice, easy way here. I can do this graphically. I can do this in a spreadsheet format. It's fairly direct. There is an example on our Canvas page. Solving for the interest rate is equally atrocious, and I will need to use my calculator or my computer to solve for the rate more often than not. So, questions? I did this as a forward value, a future value. If I do it as present value, just replace S by A, and we'll go through the same process. Just means we'll have a negative exponent in this solving procedure because it's 1 plus I to the minus N. Or you can solve it for V and get V to the N. There's another example about solving for the interest rate. I want to pull this one from the pad. Leave it's example 17. Here we go. Atypical behavior. You're saving for retirement, an individual retirement account, an IRA. Assume a $3,000 annual contribution at the beginning of each year, 6% rate of return, and then a tax bracket of 30%. Huh. This is a future value. Let's see if these numbers are 100% right. If I'm going to do that $3,000 deposit at the beginning of each year at 6% rate of return, is that ordinary or due as an annuity? There's a word right there in the problem tells me whether it's ordinary or due.
Ordinary.
Because it's exactly the reverse. Ordinary is at the end.
Oh.
Beginning is due. Your first payment is due right now at the beginning, so it's a due. So I'm going to actually set this up again in my calculator, and I'm going to say 40 payments, because it does say 40 years right here. One deposit a year of $3,000, starting with a present value of 0. Let's calculate the future value. Hit alpha solve right here. Huh. I got a problem. That's 400 and oh, wait a minute. I did something wrong. What did I do wrong? There's something on my computer screen that's wrong. I put in end. Let's go change that to beginning. Now we'll solve for the future value. All right, 492. That's not either of the numbers shown in my bar chart. What's the problem here? The problem here is that my assumption was that we were only compounding interest once a year. And it doesn't say that anywhere in the problem. So even though I'm making one payment a year, I think I'm actually making monthly interest payments. That's the way a normal bank works, right? So let's change this from 1 to 12. Then if I solve, oh, okay, that's the number I needed. So somehow in the text of all of this, there should have been somewhere a discussion that my interest is actually compounded monthly, and it isn't stated there. And that's annoying as hell. It does say that there is a 30% tax here. If I was actually doing this with post-taxed dollars, if I was putting in my money after taxes, I wouldn't be getting 3,000, I'd be getting the tax value on that, right? Or in the same vein, I'd be saying, oh, I'm really not earning 6% of that. I'm earning 70% of that. So let's take this interest rate and change it. What is my monthly interest rate? Oh, wait a second. Instead of 6% a year, it's now going to be what? 4.2% a year? But it's done monthly. All right, I got to get out of here for a second. 0.06 divided by 12. My monthly interest rate is 0.5%. Multiply that by 70% because that takes out my taxes. And then my equivalent interest rate is 1.0035 monthly minus 1, converting that to my APR. So this is the number that actually needs to go in that I. 42818, 4.2818%. A substantially different payment, isn't it? Now, I could actually say, wait a minute. What if I wanted to know the rate if I did this actually once a year? What's the APR I'm getting here? Well, it's not 6%, it's 1.05 changed. If I go up here and I solve this way, I can solve for the interest rate on here. Where's that number? Right, convert this back to 1. Then I solve up here. See how it changes my interest rate directly? So I can solve for the interest rate on a level payment annuity technologically much more directly than I can do so by hand. Solving for the interest rate's a pain in the neck. Most of the time. By the way, it is always assumed that your total interest rate should be bigger than -1, including things like taxation. This is the reason that IRAs are usually done with pre-tax dollars. So I can have the deferral of taxes and not owe money out of the front end. You'll hear more about that in the business classes. Questions? What happens if your payments aren't level? Do you have a credit card? Do you have the same amount on it every month exactly? It's really unlikely, right? Unless the only thing that goes onto that credit card is a fixed set of things like subscriptions. I don't know, maybe your Hulu and Disney Plus subscription and your Netflix subscription go on one credit card. And that's all that goes there ever. It doesn't get used for anything else. That payment's going to be whatever every month, the same. Otherwise, the payment value varies. If I am legitimately thinking of a retirement account, then I might say, hey, I expect to get a raise every few years. Maybe every year I'll get a cost of living increase. I should put some of that directly into my retirement account as well. So maybe my retirement account amount will go up every year by the same amount. Or maybe it'll go up by the same percentage. So I could have a future value In an ordinary annuity, my last payment earns no interest because it was made at the end. Where, okay, this now where the K's change. If I do the present value, I'd have that. So now the question is, can I impose upon this a pattern for the K's? And will that make my life easier? Fortunately for me, the answer to this question is yes. When the payments are made in a particular fashion. Let's go with that idea we were just talking about, where I get a cost of living adjustment or a regular raise, and I think about this pattern as affecting my K values. The cost of living adjustment, often abbreviated COLA in the news, or inflation adjustments of some type, as long as there is a percentage that everything goes up by, this is a geometric sequence. I'm going to call that the index rate, R. Let me make my life easy to start with and assume that my base payment, K, the first payment was 1. Make my life easy, right? We'll multiply by something if it's not 1. But we'll start with an assumption that our first payment is 1. Let's think about our present value. That's this formula up here. So my first payment was 1 V. I bring that back 1 period. Then I have another payment, K2, right? But K2 has gone up by that much. And it gets brought back 2 periods. The third payment has gone up again. And so on, all the way until my last payment, which has been increased for inflation adjustment by the growth of the index rate and -1 times. All right, wait a second. Factor out a V out of this. What do you notice about the thing in the parentheses? Thank God. Because I know the total of a geometric sequence. Sorry, series. So this is going to be V times. All right. 1 minus R to the N. 1 minus 1 plus R times V to the N over 1 minus R. I hate writing this in terms of V. So I'm going to change V for 1 plus I to the negative 1, or 1 over 1 plus I. Well, here that's going to be 1 plus R over 1 plus I to the N. And down here I'm going to have 1 minus 1 plus R over 1 plus I. There's a 1 plus I on the bottom here. Let's bring that into this term. What do I get on the denominator if I multiply by 1 plus I here? If I multiply this 1 plus I through on the bottom, I start with a 1 plus I times 1. And then I multiply the 1 plus I times this, it'll cancel the 1 on the bottom. What happens down there? I'm sorry.
You got the interest times the rate.
Now, the interest is the interest rate we are earning. That came from our valuation V. The R was the index rate, our inflationary behavior, the way our payments went up. So it's really the difference between those two. I've seen this before. The inflation adjusted rate calculation for the real interest rate. We had that 1 plus R, and then we had the I minus R over 1 plus R back in chapter 1. So I've seen this setup before. So this formula right here, PV equals 1 minus 1 plus R over 1 plus I to the N over I minus R. This formula is for an annuity immediate present value, where the payments go up geometrically. Now, again, 3 cheers for the ACTEC sheets, because the bottom of page 2, this formula is on the annuity sheet, right here. There's just one problem, and I don't know why the book and the formula sheet use different letters, but the formula sheet uses K instead of R for the index rate. It says right here, subsequent payments increase by a factor of 1 plus K. It's using K for the index rate. So everywhere we see R in this formula in the text, we see K here in the formula sheet. Bottom of page 2. I equal. Example 18 here sets out exactly this. I want to buy a 20-year annuity with annual payments beginning at the next year. The annuity will be valued at 11%. That's the interest rate, I. Inflation is 4%. So I want each payment to be 4% bigger. So I'm going to earn 26,000 this coming year. Next year, it should be 4% more. Year after that, it should be 4% more, and so on. This is exactly the type of annuity we just described. I'm taking into account inflation. That's the geometric growth in my payment. So I don't net lose money over time. So if that's what I'm doing, this is this formula. With that in mind, I'm not going to do the calculation. It's all there on the next page. The way we read this setup is the important part. So I understand what the formula is that I want to use. By the way, I could go through and create the future value exactly the same way, but that's a pain in the ass. So what's the shortcut to get from the present value to the future value? Present value times something. There's a multiplication by something that goes on the end there. I promise this isn't a complicated formula. I have the present value here. I have the future value here. It's n years at an interest rate of I. If I know this number, how do I get that number? Exactly. Which means for this sort of geometric annuity, I can say the future value is 1 minus 1 plus r over 1 plus I to the n over I minus r times 1 plus I to the n. But notice the 1 plus I to the n here is in the bottom of this fraction. So if I multiply that through, I get 1 plus I to the n minus 1 plus r to the n over I minus r, which is actually an easier formula, in my opinion, to work with. If you're going to be able to save $100 this year, but you're gonna get a raise of 5% next year. So you decide you're gonna put away five more, so you put away $105. The year after that, you get another 5% raise, and so on and so on. If you're earning 8% on your money, how much you're gonna have in 10 years, 30 years, 50 years when it's time to retire? This is exactly the setup. You will get a lot of financial advisors who say every time you get a raise, split it in half. Half that raise goes into your pocket for spending money. The other half of that raise should go directly to your retirement accounts. They're building this format for you. Questions? With all of this in mind, something that happens often, happens to me, is that I deposit things monthly, but my interest is only calculated quarterly. Or I deposit things monthly and my interest is only calculated annually. So what happens when my pieces don't align? Inflation is only computed once a year, but I put money away every month. What happens when they adjust for inflation only once a year, but I do the deposits monthly? So R is going to be adjusted, say, once a year, and I is going to be computed every month. Ah, huh. I'm going to have to make one of these match the other. Usually we adjust to whichever period is longer. So if I'm making deposits monthly and my interest is being calculated monthly, but my adjustments only happen once a year, I'm going to adjust monthly to annually. So here's an example. Monthly, from January 31st, 2006 through to December 31st of 2023, I put a deposit of $25 into an account earning 12% APR. Compounded monthly. It actually does say that in the problem this time. Payments rise by 12% a year. I would like to know the value in this account on January 1, 2024. Okay. If I'm going to adjust from monthly to annually, I need to do two things. I need to take my monthly payments and think of them now as a once a year payment. So here's my question for you. How much do I deposit and earn in 1 year? Let's call that annual payment X. Dude, I filled you up on Sunday. How do I figure out the value of X? Except I'm making payments every month, right? Right. It says deposit monthly. So how do I figure out the value at the end of the first year of my deposits?
Is it going to be annuity?
Yes, but which annuity? I'm thinking about 1 year's worth of payments, right? So that's a deposit of 25, and I'm going to make it 12 times at an APR compounded monthly of 12%. Now, my question is, what goes in front of that angle number? Is it an S, an A, an S dots, an A dots? Is this ordinary or due? Is this present or future?
So it's an S because it's future.
It's an S because it's future. Is it S or S dot? Just S, because I'm making my payments at the end of each month. It even says January 31st. Oh, okay. So this is what I make per year. 25, 1.01 to the 12th minus 1 over 0.01. Somebody give me a number. Three 17.062. And again, you can take as many decimals as you want at this point. I'd go at least two. I'm not going to be a geek and keep them all in my calculator, but you got as many, right? Now, that's per year in the first year. It says here that the payments go up 12% a year. That 12% a year is which rate in my formula? Is that I or R? Okay. R equals 0.12. What's I? Okay, here's the problem. It says up there that I is 12, but I is compounded monthly, right? So that means really I is 1 plus 0.12 over 12 to the 12th. Minus 1. Which is not 12%. What is that number? With a lot more, right? A lot more decimals here. I'm very glad that that's not the same as R, because in my formula for the future value, way back here, I have I minus R on the bottom. If I and R were the same, I'd be divided by 0. That wouldn't be very helpful. Now, in the formula, we actually use 1 plus I and 1 plus R in the top. The future value for my geometric is 1 plus I to the n minus 1 plus R to the n over I minus n, right? But we just worked out that I is this. If I add the 1 to the other side, it's 1.01 to the 12th. And R, 1 plus R, is 1.12. How many years did we do this for? Second, 18. So if I'm doing this for 18 years, oh, and this is for a formula, this formula assumes that my payment is 1, but we just worked out the payment per year is up here in the first year. So I'm actually going to multiply by this number. So I get my future value is 317.062 times 1.01 to the 12th to the 18th, because that's 1 plus I to the 18th minus 1.12 to the 18th over 1.01 to the 12th minus 1 minus 0.12. So that's I minus R. Give me a number, please. Tell me how much we're going to have after 18 years of doing this monthly deposit. I got a lot larger of a number than that. Yes. By the way, if you rounded to 0.06 instead of 0.062, you'd be down, I think 30 something, 40 something cents. If you keep all the decimals, I think you end up with like 0.55 instead. So it's really only a difference of a couple pennies, depending on where you round this number. Because we had a differing compounding frequency, I had to adjust. It's almost always easier to adjust the smaller one to the larger one. So if I know that my rate, maybe my inflation rate is only adjusted every 3 years. In some presidential administrations, they have not adjusted for inflation at all during an administration. We had a 0 adjustment period between, I believe, 2012 and 2020. There were no adjustments for inflation in the cost of living indices. I think that's right. Maybe it's only through 2018. So I think Trump did it once in his first term. But I have to go back and check. It is possible that this index may only happen every 3 years, may only happen every 2 years, may only happen every year, may only happen every 5 years. It depends on the properties of the administration's decisions. That difference, even though the nominal rates were the same, is important. If I is actually equal to R, we divide by 0. That doesn't work anymore. But let me go back and look at the sum for a moment. That was my present value, which factors out of V. And then I have 1 plus 1 plus R V plus 1 plus R squared V squared plus 1 plus R to the n minus 1 V to the n minus 1. But let's suppose for a moment that I equals R. What's V again? So that makes this 1 plus R over 1 plus I. If R equals I, what is that number?
1.
And so is this, because it'll be 1 squared, and so is this, because it'll be 1 cubed, and so these are all ones. How many ones are there? How many R's? How many ones? Zero, one, two, all the way up to n minus 1, there are n of them. Period. That's my present value. Which, by the way, makes the future value really easy. Wait a minute, V is 1 over 1 plus I, that's n, 1 plus I to the n minus 1. Gee, that looks familiar. It's a friggin' derivative of an exponential function. I love the power rule. So if my interest rate and my cost of living increase are exactly indexed to each other, my interest rate and my index rate match, then this calculation just literally became trivial. it is possible to use this as a pricing model for stock. A quick and dirty introduction to something we will cover more later, I hope, in chapter 9 if we get there. If not, you've at least seen it. Assume your business that you have invested in makes money and they pay you a dividend every so often. First year, it's K. Compound growth rate for the dividend is R. Interest rate for present value calculations is I. So I'm really looking at the same three ideas here. You're going to earn some money next year. That's our K value. As long as you continue to hold this stock, you will get paid a dividend. I get $13.26 every quarter from AT&T. I've held that stock since I was 5. It used to be Bell Labs back then. It was Bell Labs, it was Lucent Technologies. It's now back to being AT&T. But forever, I've had this stock for over 50 years. I've gotten dividends every quarter. So it's going to keep going forever. Instead of being an annuity, what do we call those that go on forever? So this is a perpetuity instead of an annuity, and I can use my perpetuity calculation. But I can also think of it as a geometric series. The present value is K times V plus 1 plus R V squared plus 1 plus R squared V cubed and so on as an infinite series. Wait a minute. Factor out of V, KV 1 plus R times V, 1 plus R squared times V squared, and so on. That now looks like a regular geometric series. What is the future value of a geometric, sorry, what is the sum of a geometric series? An infinite geometric series. This is a Calc 2 question. I may or may not have answered before. Yes, but in this case, A is 1, and the ratio is 1 plus R of V. I hate again, I don't like writing this in V. I'm going to rearrange this and I'm going to write it in I. So this is K 1 over 1 plus I times 1 over 1 minus 1 plus R over 1 plus I. I'm going to multiply that in on the bottom. So the K stays here and I get 1 over 1 plus I minus 1 plus R. Look how familiar that is. K over I minus R. If my dividend is going to increase at a certain known rate, and I can get some percentage on my money right now, then I can tell you what the price of this stock should be based on the dividend I get. I get $52 a year from AT&T. Savings rates right now are about 3%. What's 52 divided by 0.03? $1,733. The value of my stock in AT&T right now is $1,733. That's the value of that stock portfolio today, just based on the dividend. If my dividends were known to go up, but my dividends have been stable for the past 10 years, I'm going to assume R is 0. That's why I just divided by 3%. But if I know the dividends are going to go up, say by 1% a year, then I divide by 0.02 instead of by 0.03. Make my value more, right? Aha. So I can go through and price my stock based on what I believe the dividend will return to me as a perpetuity. There's a different example in the text on this same idea. Questions? I am not a stockbroker. Please do not take stock advice from me. But now you have what's called a rational pricing model. For a stock based on the dividend earned. And that means if I want to sell this to somebody, that's the price I should charge, because that's the money I know I'm going to earn over the life of this investment. That's what it's worth to me today. That's what I'll sell it for. Questions? This is why we're spending more time on present value calculations than future value calculations, because almost always it's like, this is what it's worth right now. So I can talk about the sale or transfer or manipulation of that asset. Again, this assumes that my valuation, my payment is going up geometrically. By the way, I did this all for ordinary. We were doing the end of the month. Please notice that if I switch from end to beginning, these formulas don't change by a lot. We just see the discount rate show up in here for the annuity due version. One of the things I used to be able to do with my retirement account here at Seton Hill was say, oh, I want you to add an extra $10 to the deposit I make every month. Then the next year I'd say add another $10 or add another $20, whatever. I could add a fixed dollar amount. I can't do that anymore. They say you have to do it by percentage. They've switched from doing strict adding to multiplying. So they make me do this geometric behavior. That's not universal. What if instead of multiplying, I just add? So let's just suppose the payment goes from 1 to 2 to 3 to 4 to 5, all the way up to n at the end. So every month I just pay one more than I paid the month before. What's the present value? Well, the present value of the first one is 1v. The present value of the second payment is 2v squared, then 3v cubed, all the way up to nv to the n. I don't like this. This is gross. I don't know what this number is. Let's give it a name. X. This is not a geometric sum. Do you remember how we got the formula for the geometric series? This formula. Do you remember getting that formula in either discrete or in Calc 2? Remember where it came from? We played a trick where we multiplied this sum by some number and then added them and subtracted them so we could cancel some stuff out. I'm going to play that game again. What if I do 1 plus I times x? Wait a minute, 1 plus I is the same as 1 over v. So I'm going to divide out of v. That's 1 plus 2v plus 3v squared plus 4v cubed plus nv to the n minus 1. If I take this one and subtract this one, what happens? 1 plus I x minus x. So take the second row here and subtract the first row. What do you get? Some very nice things happen. There's no 1 up here, so I'll get a 1. But there's a 2v minus a v. There's a 3v squared minus a 2v squared. There's a 4v cubed minus a 3v cubed. There's an nv to the n minus 1, but right before this, there should be n minus 1 v to the n minus 1. So when I subtract, I'll have one of those. This doesn't have a partner, so it'll just get stuck on the end. I've seen this before. Please notice, on the left-hand side, what do I end up with? What's this simplify to? That's this side.
Oh.
Just look at the left side for the moment. Now, this is a geometric sequence that's finite, but it starts with a 1, not a v. That happens to be a formula we've already seen in our present value calculations. If we go back here to the annuity due, I see exactly that sequence, 1 plus v, all the way up to v to the n minus 1. That's A with the dots. So that means this underlined thing is A, N, I with the dots. Hey, I just found the value. Now, this is for the present value of an annuity whose payments go up arithmetically. We use this so much that this gets its own symbol. We're going to call it an increasing annuity, present value, NI. Arithmetic increasing ordinary annuity, present value. A, because it's present value. I for increasing. If I do the future value, I get ISNI, which turns out to be S with the dots, NI. This time it's not NV to the N, it's just minus N over I. Which, by the way, because I rarely like working with the dots, we often convert these back to the non-dot formulas. In the non-dot version, this is SNI minus N plus 1 over I. Those appear directly on the formula sheet. Arithmetically increasing annuities are again a common real-life occurrence. They're worth looking at. You'll often see the phrase N payment increasing annuity. Ordinary or immediate shows up because we're doing that format. I'll do an example Thursday because I'm about to hit the clock. We have now finished chapter 2, section 2 as well. So you should be cranking on some of these problems because the list is not short. All right? I will see you all on Thursday. Have a wonderful rest of your day.